thermoelectric effect. Joule studied the heating effect of electric current and found that a current-carrying conductor produced heat. In other words, heat can be produced by means of an electric current. In 1822, Seebeck demonstrated that when two dissimilar metallic wires, say copper and iron, were joined at the ends and the two junctions were kept at different temperatures, an electromotive force was produced. Seebeck effect. The phenomenon of production of electromotive force and hence current in a thermocouple when its two junctions are at different temperatures is known as Seebeck effect or thermoelectric effect. Consider a copper-iron thermocouple. If one junction is kept hot and the other cold, it is observed that the galvanometer shows deflection, that is, electromotive force and hence current is generated in the circuit. The electromotive force thus produced is called thermoelectromotive force and the resulting current is known as thermoelectric current. The magnitude and direction of thermoelectromotive force and hence current depends upon the nature of the materials forming the thermocouple and temperature difference between the two junctions. Usually, thermoelectromotive force is very small for antimony bismuth thermocouple. It is 100 microvolt per degree centigrade. The Seebeck effect is reversible, that is, if hot and cold junctions are interchanged, the direction of thermoelectromotive force and hence current is reversed. Thermoelectric series. Seebeck studied thermoelectric properties of different pairs of metals and arranged the metal in a certain sequence called the thermoelectric series or Seebeck series. A part of thermoelectric series is bismuth, nickel, cobalt, palladium, platinum, copper, manganese, mercury, lead, tin, gold, silver, zinc, cadmium, iron, antimony, tellurium. Important features of thermoelectric series are the direction of current at the hot junction is from the metal occurring earlier in the series to one occurring later in the series. The magnitude of thermoelectromotive force is larger for metals appearing further apart in the series. Origin of thermoelectromotive force. If two dissimilar metals are in contact, more free electrons diffuse from one metal having lower work function to the other having higher work function. Thus, one metal becomes positively charged and the other negatively charged. This continues until the difference in potential across the boundary surface becomes high enough to establish equilibrium. This potential difference developed is known as contact electromotive force. The direction and magnitude of contact electromotive force depend upon what metals are used and on the temperature of the junction. When copper is brought in contact with iron, more free electrons diffuse from iron to copper, thus making iron positive with respect to copper. Hence, the direction of contact electromotive force at iron-copper junction will be from copper to iron. When the junctions of the two metals forming the thermocouple are at the same temperature, the two contact electromotive forces E1 and E2 are equal in magnitude and of opposite polarity. Hence, they cancel each other and no thermoelectromotive force is developed in the thermocouple. If the two junctions of the thermocouple are at different temperatures, the contact electromotive force at the hot junction is more than that at the cold junction, that is, E1 is greater than E2. Thus, there is a net electromotive force in the thermocouple and thermoelectric current flows from copper to iron at hot junction. It may be noted that contact electromotive force depends only on work functions of the metals, not on sizes or area of contact. Effect of temperature on thermoelectromotive force. The arrangement to study the effect of temperature difference between the two junctions of a copper-iron thermocouple on the magnitude of thermoelectromotive force is shown in the figure. Keeping the temperature of the cold junction B constant at 0 degrees Celsius, the temperature of the hot junction A is gradually increased and corresponding readings of the galvanometer are noted. Note that deflection of the galvanometer is directly proportional to the thermoelectric current and hence to the thermoelectromotive force. The graph between thermoelectromotive force and temperature of the hot junction has a parabolic shape. The main features of the graph are when the two junctions are at the same temperature, say 0 degrees Celsius, the thermoelectromotive force is 0. As the temperature of the hot junction is increased, keeping cold junction at 0 degrees Celsius, thermoelectromotive force also increases till it becomes maximum at temperature theta n. The temperature of the hot junction at which the thermoelectromotive force is maximum is known as neutral temperature theta n. The neutral temperature depends upon the nature of metals forming the thermocouple. For a particular pair of metals, its value is constant and is independent of temperature of the cold junction. Thus, for copper-iron thermocouple, the neutral temperature is 270 degrees Celsius irrespective of the temperature of the cold junction. As the temperature of the hot junction is increased beyond neutral temperature theta n, thermoelectromotive force starts decreasing and ultimately becomes 0 at temperature theta I. The temperature of the hot junction at which the thermoelectromotive force is 0 and changes its polarity is known as the temperature of inversion theta I. If the temperature is increased beyond theta I, the direction of thermoelectromotive force is reversed. It is due to the fact that the number densities and rates of diffusion of electrons in the two metals used are reversed. The inversion temperature depends upon A. The temperature of cold junction and B. The nature of metals forming the thermocouple. Relation between theta n and theta I. The temperature of inversion theta I always exceeds the neutral temperature theta n by the same amount as the neutral temperature exceeds that of the cold junction theta c, that is, theta I minus theta n is equal to theta n minus theta c, or 2 theta n is equal to theta I plus theta c. Therefore, theta n is equal to theta I plus theta c upon 2. Relation between thermoelectromotive force and temperature. The thermoelectromotive force of many pairs of metals have been measured as a function of temperature of hot junctions theta. In every case, if the cold junction is maintained at 0 degrees Celsius, the thermoelectromotive force E will be E is equal to alpha theta plus 1 upon 2 beta theta square, where alpha and beta are constants and their values depend upon the nature of materials forming the thermocouple and the temperature difference of the two junctions. The graph between thermoelectromotive force and temperature of hot junction is a parabola. Thermoelectric power S. The rate of change of thermoelectromotive force with temperature is called thermoelectric power or Seebeck coefficient S, that is, thermoelectric power S is equal to differentiation of alpha theta plus 1 by 2 beta theta square with respect to theta is equal to alpha plus beta theta. The graph between S and theta is a straight line. S is equal to alpha plus beta theta. For theta is equal to 0 degrees Celsius, S is equal to alpha, that is, thermoelectric power is independent of the temperature of cold junction. Expression for neutral temperature theta n. The thermoelectromotive force E is equal to alpha theta plus 1 upon 2 beta theta square, or dE by d theta is equal to alpha plus beta theta. Equation 1. Now, neutral temperature is that temperature of hot junction at which thermoelectromotive force is maximum. Therefore, at neutral temperature, dE by d theta is equal to 0 and theta is equal to theta n. Therefore, from equation 1 we have 0 is equal to alpha plus beta theta n, or theta n is equal to minus alpha upon beta. The thermoelectromotive force E is equal to alpha theta plus 1 upon 2 beta theta square. At temperature of inversion, E is equal to 0. Therefore, 0 is equal to alpha theta I plus 1 upon 2 beta theta I square, or 0 is equal to theta I into alpha plus 1 upon 2 beta theta I. Since theta I cannot be 0, alpha plus 1 upon 2 beta theta I is equal to 0, or theta I is equal to minus 2 alpha upon beta. Example, in a certain thermocouple, the thermoelectromotive force E is given by E is equal to alpha theta plus 1 upon 2 beta theta square, where theta is the temperature of hot junction. The cold junction being at 0 degrees Celsius, alpha is equal to 10 microvolts per degree centigrade and beta is equal to minus 1 upon 20 microvolts per degree centigrade square. Find 1. The neutral temperature and 2. Temperature of inversion. Solution. 1. Neutral temperature. Since thermoelectromotive force E is equal to alpha theta plus 1 upon 2 beta theta square. Or dE by d theta is equal to alpha plus beta theta, when dE by d theta is equal to 0. Theta is equal to theta n. Therefore, 0 is equal to alpha plus beta theta n, or theta n is equal to minus alpha upon beta is equal to minus 10 upon minus 1 by 20 is equal to 200 degrees Celsius. 2. Temperature of inversion. Theta n is equal to theta I plus theta c upon 2 is equal to theta I plus 0 upon 2. Therefore, theta I is equal to 2 theta n is equal to 2 into 200 is equal to 400 degrees Celsius. Thermoelectric thermometer. Thermoelectric thermometer is basically a thermocouple and is used to measure both low and high temperatures. Its operation is based on Seebeck effect. The selection of two metals to form the thermocouple depends upon the range of temperature measurement. Thermocouple, copper, gold and iron alloy. Range of temperature 1 Kelvin to 50 Kelvin. Thermocouple, copper and constant. Range of temperature 30 Kelvin to 400 Kelvin. Thermocouple, platinum and platinum iridium alloy. Range of temperature 400 Kelvin to 1300 Kelvin. Thermocouple, platinum and platinum rhodium alloy. Range of temperature 1300 Kelvin to 2000 Kelvin. Construction of thermoelectric thermometer. A thermoelectric thermometer consists of two wires forming the thermocouple. These wires are welded together at one end and this end forms the hot junction. The portions of wire near the hot junction are insulated from each other by enclosing them in hard glass capillary tubes CT. The wires pass through mica discs arranged one above the other in a porcelain tube T. The ends of the wire are connected to terminals T1 and T2 at the top of the porcelain tube. To the terminals T1 and T2 are connected two leads, L1 and L2, called compensating leads of the same material as those of the wires forming the thermocouple. The leads are taken to a convenient place and welded together to form the cold junction. The cold junction is immersed in ice to keep it at 0 degrees Celsius, 273 Kelvin. A sensitive millivoltmeter may be inserted in the thermocouple circuit to measure the thermoelectromotive force. Theory of thermoelectric thermometer. By keeping the hot junction at different temperature, cold junction being at 0 degrees Celsius, the corresponding thermoelectromotive forces are noted from the millivoltmeter. A graph between the temperature of hot junction and thermoelectromotive force is plotted. The body whose temperature is to be determined is placed in contact with the hot junction, cold junction at 0 degrees Celsius. The thermoelectromotive force produced in the thermocouple is measured by millivoltmeter. Using the curve, the temperature of the hot body can be found corresponding to the measured thermoelectromotive force. Advantages of thermoelectric thermometer. As the junction is very small, therefore it absorbs only a small amount of heat from the object. Consequently, the temperature of the object does not change. It has low thermal capacity and, therefore, quickly attains the temperature of the object. For this reason, A thermocouple can be used to measure fluctuating temperatures. Because the electrical nature of measurement, it is an accurate method. A thermocouple has a very large range from -200 degrees Celsius to 1500 degrees Celsius, depending upon the metals used. They are very sensitive and can measure temperatures up to 0.05 degrees Celsius. They are cheap and can be constructed easily. Disadvantages of thermoelectric thermometer. As the output voltage is less than 10 millivolt, a very sensitive voltmeter is required. These thermometers are not direct reading thermometers. Therefore, they cannot be used in experiments on calorimetry. Temperature of the cold junction has to be kept constant. For the measurement of temperature of different temperature ranges, different thermocouples have to be used. Applications of thermoelectric effect, thermopile. By arranging several thermocouples in series, a sensitive heat detecting device called a thermopile can be made. Since the thermocouples are connected in series, the electromotive forces are added up. This increases the net thermoelectromotive force and hence thermoelectric current. The arrangement of detecting heat radiations by a thermocouple is shown. Thermopile. A number of series connected bismuth antimony thermocouples are housed in a horn-shaped vessel. One set of junctions, junction A, is painted black to absorb radiations and so becomes hot more easily. The other set of junctions B, is well polished and covered with insulating lid. This set therefore remains cool. The free ends of the thermocouples are connected to a sensitive galvanometer. Working of thermopile. When heat radiations fall on the horn-shaped end of the thermopile, the temperature of junctions A is increased relative to the junctions B. Consequently, thermoelectromotive force is produced in each thermocouple. These electromotive forces add together to give an appreciable output. The galvanometer is generally so calibrated that it directly gives the temperature or intensity of heat radiations. This instrument is so sensitive that it can detect the heat from a lighted matchstick some distance away. Thermoelectric refrigerator. The working of thermoelectric refrigerator is based on Peltier effect, that is, if current is passed through a thermocouple, heat is evolved at one junction and absorbed at the other junction. If on the whole the process results in the removal of heat, we have a thermoelectric refrigerator. It can be used when the region to be cooled is small and noiseless operation is required. Thermoelectric generator. The working of a thermoelectric generator is based on Seebeck effect. By heating one junction of a thermocouple and keeping the other junction at ambient temperature, electric current can be generated. The electric power thus generated may be used to operate electronic devices in remote areas.